Okay, we've made it to the last section of Unit 1. We're going to be talking about improper integrals. And improper integrals you can think of as an extension of the definite integral as we know it. There are two fundamental types that we focus on in this course. And the first type is one that we can kind of already imagine pretty easily. And it'll be clear once we talk about motivating example. But fundamentally, these are integrals that arise when we have an infinite interval. So instead of having some two real numbers a and b that form the lower and upper bounds of the interval for which we integrate, we're going to be finding area over an infinite interval. And you may think, well, that should be infinite, right? Not necessarily. So we'll see a really cool example of when this gives us an actual real number. And there are some really cool applications here that are gonna pop up in the next unit when we talk about probability. So here, our motivating example comes from radioactive decay. And we kind of have already seen some of these examples. Particularly, we talked about the model for decay. So if we're given mass at time t of a decaying substance from the time point where we start measuring to forever. So our domain for this model is from 0 to infinity, and we have the function m of t equals m naught e to the kt, where we assume k is a negative number called the decay constant, and m naught is initial mass. Now this is new. We've covered this. We've talked about how this model arises and what it means. So the function decays over time. I'll just graph it briefly so you can see what that looks like. So it typically looks like this, something like that. Eventually it decays to 0, so we know two things here. We know m of 0 equals m naught, which is this point, right? And we know that the limit as t goes to infinity of this function goes to 0. So eventually it diminishes to nothing. But we can define the mean life of an atom in this substance as the area under the curve negative kt, e to the kt. Now, we're not going to talk about how this arises yet, but mean life, actually, this is a term synonymous to the expected value of a random variable. Again, we're getting into some applications that we're going to talk about much later. But we would write then, capital M is, and this is defined over the entire domain. So this would be the integral, I pulled out the constant first. So negative k times the integral from 0 to infinity of t e to the kt dt. But what does that look like? Does this even exist? Does this make sense to write? If such an m exists. And so in theory, this is a modification, of course, of the actual function that we started with. But in theory, it seems like what we're talking about here is just some curve that looks kind of like this, going all the way out into infinity. And we're talking about computing all this area all the way out to infinity. So that's an infinitely long tail there. And we're supposing that that area is M. Okay. So our objective in this video then is to establish, formally define how to interpret this statement and actually calculate it. Okay, so here we go. Incoming definitions. Okay. So we define the integral from a to infinity of f of x dx. In other words, the area under the curve from a to infinity, as the limit as t approaches infinity of the integral from a to t of f of x dx. Okay, so some important pieces to highlight here. This t that appears, right, is kind of a dummy variable. It's not, though. It means something. Okay, so it seems like we're just kind of writing something, in a more complicated way for no reason. But if we formally define it this way, then we're using the power of our tool bag for limits to say something conclusive about this kind of object. So we define this as long as the limit exists. We would say that this improper integral being the name of this kind of object, converges to a real number. Otherwise, if the limit doesn't exist, we say the integral diverges. So let me show you what that would look like. Let's interpret this, okay? So visually, what are we talking about here? Okay, let's suppose I have this function. Sure, why not? Looks sort of like this. And here's my value, here's my number a. And so I'm going to set some t, which is going to be some arbitrarily large t. And that's going to be my upper bound. Okay. Then what I'm shading here in red is this quantity here, the definite integral from a to t. Now, what we're saying here is that we're taking the limit of the tail. So this improper integral of f of x dx from a to infinity is the limit of the tail as t goes to extends out to infinity. And so we hope that as t gets very large, the additional pieces here that we're adding, for instance, something like this amount to some new t, t1, we're hoping that this amount ends up being negligible in the long run. But this is that first version of this definition. And we can similarly define, so we can extend the definition. We can similarly define the integral from negative infinity to b of f of x dx is going to be the limit as t approaches negative infinity of t to a of f of x. So same idea, except the limit is on the left. Technically, these are left-hand and right-hand limits, respectively. But again, provided the limit exists. If the limit exists, we say the integral converges. If it doesn't, the integral diverges. And we can go one further. We can define the integral from negative infinity to infinity of f of x dx is the limit from negative infinity to a of f of x dx plus the integral from a to infinity from f of x dx, where a is any number we want, so pick any a. As long as it's finite. You can pick 0 or some convenient number that splits it. And this only works provided all the limits exist. If one of them doesn't exist, then the whole thing goes to infinity and it blows up, it diverges. Okay, so this only exists if both of these two improper integrals that we split it up into converge. Okay, importantly, we assume f is continuous over the entire real line. Okay, this one doesn't, or whatever infinite interval we're talking about, for instance, a to infinity. Sometimes we write the integral from negative infinity to infinity of f of x dx as the integral over r of f of x dx. So remember that blackboard r represents the real number line. And so what we're saying here is we're integrating over the entire real number line. And this has implications for further branches of math that you might explore. But just know that you might encounter that notation from time to time. Okay, now that we've done all that, let's actually see an example. Let's get our hands dirty. Okay, so we're going to determine whether the improper integral of 3x plus 1 cubed dx over 3x plus 1 cubed from 1 to infinity converges or diverges. And if it converges, we evaluate it. So there's two scenarios here. One, it converges to a real number, and we have to state what number it is. Or we know that it diverges, in which case the integral literally will become infinity. So let's go ahead and do this. So we'll rewrite it using the definition. So that means we're going to replace the infinity symbol with t, and we're going to take the limit as t goes to infinity. And this feels like we're just, waving our hands and making it a little more complicated than it needs to be. No, I promise it matters. Without doing this step, you cannot exploit the important properties of limits. So here we're going to need to do a substitution. So we're going to let u equal 3x plus 1, which means du equals 3 dx. We're going to plot a 1/3, okay, importantly. And the limits are going to transform as well. U of 1 becomes 4, and u of t becomes 3t plus 1. One really important thing to note here, which is we're going to whoosh away that detail for, all the time, just because it's never going to come up, but if u were not a continuous transformation of x, then there would be some weird limit things going on here. But because it is a continuous transformation of x, then we can just go ahead and continue with the substitution here, right? So that means this integral becomes the limit as t approaches infinity of the integral from 4 to 3t plus 1 of 1/3 times du over u cubed. Okay. Now, let's forget about the limit for a second and just focus on the integration. So the limit as t approaches infinity of 1/3, I'm going to pull that out. The integral from 4 to 3t plus 1 of du over u cubed. Power rule, so that's going to turn into negative 1 over 2 u squared from 4 to 3t plus 1. 1/3 still out in front. Limit as t goes to infinity. Okay, here's where we can start to do some things that, we're comfortable with. So there's a negative 1/2, that's a constant term really, and then there's 1/3. And we can pull that all the way out and make that a negative 1/6 limit as t approaches infinity of 1 over u squared evaluated at 4 and 3t plus 1. Okay, so don't forget about the negative 1/6 out in front. But at this point, we're using FTC2, which means we're going to plug in our b, which in this case is the 3t plus 1. 3t plus 1 squared minus 1 over 4 squared, which is 16. Okay? Good so far? Okay. Then, what happens when we apply this limit? So this is a constant that's going to stay the same. Okay, so we don't have to worry about that. As for this expression, when we plug infinity into that, because the denominator is a polynomial and the numerator is just a constant, then this means this goes to 0 by dominance. This means that all we're left with really is negative 1/6 times negative 1 over 16, which is, what would that be? 6 times 16 is 96. 1 over 96. That's our answer. So it converges, and the answer is 1 over 96. Okay. Let's do another example. Same idea. We're going to determine whether the integral from 1 to infinity of ln of x over x dx converges or diverges. If it converges, we're going to evaluate it. Okay, so let's go into it. So our integral that is expressed, we would say improperly. We're going to replace it using the definition. So the limit as t goes to infinity of from 1 to t of ln of x over x dx. Again, we need a substitution here, but this substitution is not complicated. I hope that at this point you're, really being really cognizant of all the strategies that we need to use for integration. So we're going to let u equal ln of x, which makes du be dx over x. Convenient, because we're going to be left with u du. And this is a continuous transformation of x, so we won't have to worry about any limit stuff. So this becomes the limit as t approaches infinity of the integral from ln of 1 is 0, ln of t is ln of t, of u du. Then this means the limit as t goes to infinity of u squared over 2 from 0 to ln of t, which leaves us with the limit as t goes to infinity of ln of t squared squared over 2 minus 0, which is nothing. And this, unfortunately, diverges because ln of infinity is infinity. Because it equals infinity, the integral diverges. And that's our answer. So now you see, when the integral diverges, you get something with an infinity in the limit. Okay. So that said, let's come back full circle. So application problem that we started with, we wanted to compute the mean life, or to understand how mean life works for a particular function. So suppose we have some mass function equal to 100 e to the negative 2t. So in other words, k equals 2. Or negative 2, I should say. Okay. Then, for this model, the mean life of an atom is given by m being 2 integral from 0 to infinity of t e to the negative 2t dt. All right, so now it's our task to find this integral. It's an improper integral, and we need to use integration by parts here. So we're going to let u be t, dv will be e to the negative 2t. Now we're using t here, which means that when we change this into into the definition of the improper integral, we're gonna have to use a different letter. So just be aware of that. All right, so then du equals dt. So this is not the same t that we're gonna take the limit of, I guess is what I'm trying to say. V equals negative 1/2 e to the negative 2t. I guess there was a dt missing from that dv statement. All right, so let's go ahead and write this out. M is 2 times the limit as, and we're going to use a different letter here. Let's use b, as b goes to infinity of, and now we're going to convert that integral. So we're going to use the integration by parts step. So u times v is negative 1/2 t e to the negative 2t minus the integral of u times dv. Sorry, v times du. Negative 1/2 e to the negative 2t dt, evaluated all from 0 to b. Okay, so b is the thing that we're going to take the limit of. Let's clean that up a little bit. So 2 times the limit as b goes to infinity of negative 1/2 t e to the negative 2t. What should that be? Minus 1/4 e to the negative 2t from 0 to b. I'm going to clean that up even further by writing what's inside as e to the negative 2t times negative t minus 1/2. I'm pulling out a 1/2 now, and that'll cancel with the 2 in front. So limit as b goes to infinity of this expression now from 0 to b. So the b, and I pulled out a 1/2, and that canceled with the 2 in front. Okay, then this becomes the limit as b goes to infinity of e to the negative 2b times negative b minus 1/2 minus e to the 0 times 0 to negative 1/2. Or sorry, 0 minus 1/2. Okay. So where are we at? Where are we? So let's distribute the e to the negative 2b. So the limit as b approaches infinity of negative b e to the negative 2b minus 1/2 e to the negative 2b plus 1/2. Okay, I'm going to rewrite the negatives the negative exponents, as I'm going to write it as negative b over e to the 2b minus 1 over 2 e to the negative 2, sorry, to the 2b. Plus 1/2. That'll make it easier to see what's going on once we take the limit. So in the limit, this is an indeterminate form because we get infinity over infinity. We're going to need to use L'Hopital's rule. This term goes to 0, and this term stays the same. So I'm going to use L'Hopital's on the first expression. That's going to be the limit as b goes to infinity of negative 1 over 2 e to the 2b plus 1/2. And now we can see that the indeterminate form that we converted using L'Hopital's rule, that actually turns into 0. And lastly, we get 1/2. So there you go. This means that